Welcome back to Just in Time and TOC, or Theories of Constraints, Philosophies of Improving Operations. Let's start taking a look at a little bit of a historical perspective. Henry Ford was actually the first one to truly use an assembly line, and he used it to produce a small, simple, reliable car that many could afford. And, you could have it in any color you wanted as long as it was black. So he started with this idea of assembly line processing, really put it to use. And I hate to say it, but after World War II, rebuilding of Japan, we sort of gave them the idea of just in time, of working with this principle, and they ran with it, especially the Toyota Motor Company, who really used research and applications to work with just in time to make it work for them and to improve on the systems where, lo and behold, the United States was not doing that. So if we take a look at this just-in-time philosophy, what does it involve? It starts with people involvement. It's teamwork. It's people working together, not just you, but everyone. I don't care if you're Susie Q, the CEO, or Joe Schmo, who's mopping floors. We're taking a look at everyone working together to make sure that the company runs well. It's a discipline. You must be disciplined to use it. It's not a fly-by-night. Otherwise, you're not going to have stuff just in time, and you're going to have things that are waiting, not there when you need it. You're going to have production shut down. You'll have things go bad because they're not there or you have too much. And you really need to just create a supplier partnership, and this is called JIT 2. Just in time 2 is creating a partnership with your suppliers to ensure you have quality products on time when you need them. Because if you don't have the quality product, then you're going to have a lot of scrap, you're going to have rework, you're not going to be able to create the quality that you want to create in your product, and it becomes a major issue in just in time. You need total quality control, TQC, where quality is everyone's job. It means that anyone can stop the procedure. Everyone is working to make it better. You work toward what's called an immediate customer. If we're taking a look at something that has 3 stations, station 1, station 2, station 3 to get it done and produce, then station 2 is the immediate customer of station 1. They need to produce a quality product for station 2 to be able to do their job. That's that immediate customer, that next person in line that's going to work. Where it might be seen as work in process, it's actually you're completing your part of your job. You're completing the part of the finished product that you do, even though it's not the complete finished product, and that next person takes over. So you need to create quality work for them to be able to do their job. And we'll take a look at quality at the source. Each employee is given a responsibility for quality at their workstation. Each employee is able to say, we're not going to do this. This is not right. We need to shut down. We need to realign. We need to fix. We need to do something instead of just making it. Employees are trained in a quality principles and testing procedure, and it's called Shidoka. Make nothing rather than making it incorrect. My mother always said, if you can't do it right, don't do it at all. So, and it's this idea. We want to make good quality products. So if you're not going to make that, don't do it. And you should probably go get another job. It becomes a culture, not just a program. It's a way of life. And it has to become the culture, the way the company runs itself to be fully effective. You need to work towards total quality as a consistent, pervasive, continuing activity. It's never good enough. But how can we improve on it? How can we make higher quality products? How can we make better products? So we take a look at just-in-time's workflow and the advantages that this has. Why use just-in-time? Well, if we have excessive work-in-process inventories, it can hide serious problems. When you have stuff waiting in queues, waiting in lines, we don't know what's going on there. We don't know if it's high quality because that next person doesn't have it. They're not working on it. So we want to make sure that it reduces the queues because they're a waste, and we discover any problems in a time that we can get them fixed. We know instead of producing multiple bad products, we produce 1 or 2, and we can fix the problem, create a solution, and we end up now reducing cost for rework, cost for scrapping stuff. And even if it's a true design, we need to do the whole different design with this. This is why we want to use just in time. We want to reduce those costs. We want to discover the problems, and we want to fix the problems in a just-in-time right now instead of later, instead of having them wait. Some elements that support our just-in-time flow are focus factories. Focus factories are set, uniform production rate, and mixed model assemblies. We take a look, we're going to talk later about having a drum beat, and that's what this looks at. We use, instead of pushing stuff through, look at how many I can produce, we're actually going to use a pull method. We're going to use MRP and adapting it for just in time. So we're going to say, how many should I produce of this part of it? If I'm producing a chair and I'm putting the seat back, I'm covering them with putting the foam and the material and putting together the seat backs, how many seat backs do I need to produce so that we have X number of chairs? And I take a look at a Kanban system. These are production cards and move cards. They tell me to stop or go. It tells me to produce. Here's a card that says green. It means produce. Once I produce a certain amount, I pull it over. It's stop. I don't produce anymore until somebody pulls this away and flips my card back over again and tells me to produce again. That way, I'm not producing just for the sake of producing, which is not good. Production and procurements are in small lots. We want to figure out what the minimum feasible lot size is. That doesn't mean because I can produce 200 at a time, I should be producing 200 at a time. Maybe I should only produce 20 at a time. What is best? Maybe I can only produce 20 at a time, but my lot sizes for delivery, which means I might need to produce bigger lot sizes for delivery, which means I produce my 20, then another 20, then another 20, then another 20 until I have 100 ready to be moved. And my move card isn't there. It doesn't say go, pull away. I'm stopping production until this time, until you move this stuff away. My delivery lot is ready. I don't produce more until after that again is pulled away. But sometimes I need to do more than one lot size to get to that point. I need quick, inexpensive setups. Now, we talked before that the setup cost, even though in accounting is seen as a fixed cost, it really isn't. We want to reduce our setups cost as much as possible. We constantly want to reduce those numbers there. So we want simple, quick, inexpensive setups so that we have a reduction in costs there. We want multi-skilled workers who can do more than one thing. A lot of times with automation, we're able to see that there are so many things that a worker can do, so they're not just standing around because the machine is taking over more and more of the jobs. Flexible factories allow us to produce more than one item. In a factory, we can make changes. If you go to Krispy Kreme, they actually make donuts in different sizes. They make donuts with the holes in the middle. They make that are just glazed or frosted. Then they make donuts that don't have the holes in the middle that are filled with lots of good stuff. So, they're doing that. They can make big donuts, little donuts. They're able to do this with quickly changing the die cut on the extruder process. You want high quality levels. Smaller lots can mean fewer defectives are made before they're discovered. And that's what we want to do. So they're discovered in time to investigate what happened. Stuff isn't just sitting around. We want to know what happened, what went wrong, and we can figure this out so we don't continue to make defective products or low quality products. We want that high quality. We want effective preventative maintenance. When you're making smaller lot quantities and you're not having the extra there, then there's not really downtime that you can have for major repairs. So you want to take the time to do maintenance. How many of you drive a car? Do you change your oil? If you don't, the rods can go. It's not good. That happened to me. Don't let that happen. I now change my oil every 3,500 miles. Do you check that? Do you oil things? Do you put gas in the car? If you don't put gas in the car, it doesn't go. These are, effective preventative maintenance things that you need to do to make sure that things are still working. Rotate tires, change tires when they become bald so that you don't slip and slide on the road. All of these effective type maintenance things that you do with your car, take that over into the work. Do you need to oil the equipment that you're using? Do you need to clean equipment? Do you need to change belts on equipment? These are all things so it doesn't break down that you need to take into consideration. And workers take pride in maintenance and learn to repair some problems themselves. It's not just a maintenance worker, but people are able to do small repairs on their own, and they take pride in that. Next, they continually work to improve. Always looking for a better way. How can we make this better? How can we do better? How can we improve our quality? How can we lower our cost? How can we reduce our price to our customers? This way, just in time becomes a competitive weapon. It allows your job, your company, your product to be better than your competitors, lower price, higher quality. These things that you're taking a look at is the best. It's great ways for you to improve, and it becomes a weapon. It becomes a way for you to compete in the marketplace. Looking at the theory of constraints, if you have not read The Goal by Eliyahu Goldratt, I suggest you do. It's an easy read, excellent book, and it really does talk about the theories of constraints very well. So just to give you an idea about this, which you can get this book and read it more in depth if you'd like, the theory of constraints is actually a management philosophy. And what we're looking at is identifying problems and developing solutions to those problems. So we want to take a look, what is the problem? And the theory involved from a method developed in Israel by Eliyahu Goldratt and his associates to schedule maximum output from a plant whose demand exceeded its production capacity. How do you meet a demand that's greater than your production capacity? They found a way, and they used this theory of constraints to break down constraints, things that were stopping their capacity from growing, to be able to do this and create a higher capacity in their plants. This has been applied to operations in education, healthcare, manufacturing, service, across the board. It's a very important theory. So there's 5 steps to the theory of constraints problem solving. The first is to identify the system's constraint. We're looking at that bottleneck. Where's the bottleneck? Where's the constraint? What is preventing us from producing more? And describe how to exploit the system's constraint. How can we alleviate this constraint? How can I exploit it so it no longer is a constraint? We want to subordinate everything else into that decision. How can I get rid of that constraint? How can I get rid of that bottleneck? And elevate the system's constraint so it's no longer a constraint. Although you do have to check and make sure in this last step, step 5, to make sure that that constraint has been broken. If that constraint has not been broken, then you didn't do something to exploit it in that second step. Go back and try again. So you want to identify the constraint, exploit it, figure out how to make it so it's not a constraint, subordinate everything else to that decision, and then evaluate it again to make sure that you did break that bottleneck, break the constraint. And you can continually complete these steps. If the constraint has been broken, you're going to identify another constraint, because there's not just a constraint in a system. There are multiple constraints in a system, and you need to break each one as you go along. You need to know what a bottleneck is. It's a resource whose capacity is less than or equal to the demand placed on it. We look for a drum. Your constraint is actually what establishes a drumbeat for synchronizing the work on other resources. In other words, if this is the time, this is how fast that constraint can go. This is how fast everything else should go. It establishes that beat, that marching beat, how fast things can go, because it becomes very important so that you don't have excess work in process, so you don't have things and problems sitting around waiting in a queue to be found out later on. A time buffer is the amount of time a material will be scheduled to arrive at an operation ahead of when it's expected to be used. A time buffer is safety stock in traveling. If you think that you have stuff in a warehouse and it has to get into the plant to the equipment that it's going to be using onto that station where we're going to do that work, how much time do you want it there in advance? 5 minutes in advance, 1 day in advance. You want to make sure that things aren't sitting around. So you really want to take a look to see how soon you can get that done. So when we take a look at the theory of constraints and the principles, what do you want to do? Balance flow, not capacity. Start with taking a look at the drum beat. That's the set of the flow. That's the pace things need to go, not capacity. You don't want to produce something at a workstation as much as it can, because utilization of a non-bottleneck should be determined by some other constraint. So if it's not a bottleneck, something else should set the pace for it so it's not producing, because utilization and activations of a resource are not synonymous. Activation is the time spent running units on a machine or other resource, whether they're needed or not. If you're able to work this station, this workstation on this resource, and you're able to produce, things are going flying out. You're able to get it done. Look at how many I can make, but they're just sitting there. That's not good. You want to utilize your resources. Running a resource in accordance with the rate at the bottleneck, the drumbeat. Remember? The constraint is that drumbeat. It's what you want to use to be able to get things done at the flow so that you're not creating a problem and it's sitting there that you don't realize until later. Remember that. So an hour lost at a bottleneck is actually an hour lost for the entire system. If the bottleneck breaks down, that constraint breaks down and time is lost there, it's actually the whole system that's going to hurt. But an hour saved at a non-bottleneck is nothing more than a mirage, because all you're doing is producing for stuff to sit around and sit in queues, and that's not good. So it's your bottlenecks that should govern both your throughput and your inventory. Your bottleneck is what takes a look at the capacity on how much you can create. You want your transfer batch size not necessarily to be equal to the process batch size. At a non-bottleneck, your process batch size might be half of its capacity of what it's actually able to do. It might be that your bottleneck is able to take 100 units, but you're only at this station, you're only able to, at this resource, produce 20 at a time. So you might have to produce 5 before you transfer. So you might do 5 batches before you transfer. So transfer batch size and process batch size don't always equal. The process batch should be variable, not fixed. Just because you can make that many doesn't mean you should. Again, utilization versus activation. Schedules should be established by looking at all constraints simultaneously. We're taking a look at more than one constraint. Yes, we want to take a look at one constraint at a time to try to break it, but we have to figure out what the multiple constraints are, because it might be in different areas that we can work on 2 constraints at once or 3 constraints at once. So we're taking a look at all the constraints simultaneously to see which ones should be broken first, or how many we can break at the same time to move things along so we don't have things waiting in a queue. This is our look at just-in-time and theory of constraints. Like I said, The Goal, written by Eliyahu Goldratt, is an excellent book to go further deeper into the theory of constraints. And like I said, it's a very interesting, it's a quick read. I think you'll enjoy it. So why don't you take a look at that? Have a nice day, and we'll be back later talking about quality control.